All right, hello everyone. Welcome back to Machine Organization and Programming. This is the last lecture of the class. All right, I know the middle was a little rough when I got sick, and then I never really got caught up. I really hope I didn't cram too much stuff into the very end there. It's a big part of the reason why I wanted to delay this lecture and then do it after the final. So I didn't want to have too much stuff, overwhelm everyone. I know that summer classes go at a really fast pace, and they can be really challenging because of that. This semester was really great for me. I actually met 53 of you guys during video chatting over my office hours. I think this is actually more students than I met during the spring semester when I had twice as many students in like a real person class. Anyway, so today, the final lecture, we're just going to go ahead and do a quick introduction to operating systems. I feel like this is really the last topic that would be included in a machine organization class. It's just something to get the flavor of an operating system, talk about the major things that they do as it relates to machine organization. I highly recommend you guys all go take operating systems, and I hope this is a good introduction to make some of those topics a little easier. All right. I thought I'd just start with a quick overview of the course. When we first began that very first lecture, I talked about some of the things we're doing. The first third of the class was devoted to learning how to program in C. And then the second third, we took a look at when the C program is compiled into assembly, what's going on there, what is really happening at the level of the registers, assembly code, memory management, those sorts of topics. And then for this last third of the course, I wanted to deal with some more system level kinds of questions. And we talked about dynamic memory allocation, how memory is actually allocated on the heap. Project 5 was devoted to writing our own. We delved into cache memories and talked about how the system takes advantage of different types of memory hardware to make things go faster by bringing the instructions and data we need closer to the CPU. And finally, the last topic is going to be operating systems. So I brought back another slide from the very first lecture, my How Computers Work slide, to sort of introduce the idea of operating systems. We all are familiar with Windows and Linux and Mac OS that we all have on our computers. But if we had to describe an operating system in really general terms, I'm going to put it into this sort of picture here, where we have our application programs at the very top level. These are things the user wants to run. Our word processing, our web browsing, our C programs that we write, our notepad, our video recording software, our video editing software. I've got another half dozen things open right now. But then at the very bottom level, we've got the hardware, the CPU, the memory, our disk drive that all takes care of running all of those programs. And in between, the operating system is going to be responsible for figuring out how this all fits together. We've got to share all these resources, the CPU, the memory, the disk, between all the programs that are running. So an operating system is just a program that runs on our computer. It's a program whose job is to manage the computer resources and provide common services needed by applications. So it's going to manage the CPU, it's going to manage the memory, it's going to manage the input-output, and it's basically a program that's just going to make our computer much easier to use. Right now, I've got a dozen programs running, but I only have one CPU. It's a multi-core CPU, but I still have to worry about sharing all of those programs with just that one CPU. Yeah, these programs also have to share all of the memory and do it in a way that they don't conflict with each other. So the operating system is going to take care of the details of allowing my computer to run two or more programs at the same time. So really the two topics that I want to take a look at, the two topics from operating systems that really apply to what we've been talking about all semester, is basically running two programs at the same time, considering that we may only have one CPU with one core, like older computers would. So we have more programs than we have CPUs. And the other issue that we're going to run into is that the memory address space is this continuous block of memory addresses from 0 to some address, some maximum address. And every single program that runs thinks it can use all of the memory. Now, if we're running more than one program, they do have to share. So that's the topic of this lecture, is how does the operating system take care of these details so that we can have two programs that run simultaneously? And just to give this some more grounding, I pulled up another slide from the very first lecture. where I was talking about what does the CPU do. The CPU is very simple in terms of its operation. It's going to go get an instruction from memory. It's going to look at the instruction pointer, grab that instruction, and pull it in. It's going to decode it to figure out what to do. Then it's going to execute that instruction. Then it goes and gets the very next instruction. Most likely the next instruction in sequence, but if the instruction that we just executed was a jump, it could be somewhere else. But it just does this loop forever. I hope you realize at this point that the programs we've been writing run by themselves. Nowhere in any of those programs do we say, okay, it's time to switch to another program. Here's an instruction. Let's go let someone else have the CPU for a while. All of those details are taken care of by the operating system. The programs that we write pretend they have the illusion that they have the entire CPU to themselves and never have to share it. That's known as CPU virtualization, and the operating system takes care of that. The way it does this is known as time sharing. Essentially, the operating system is going to switch back and forth between programs or processes very quickly. It's going to give one program 10 milliseconds, switch to another one, give that 10 milliseconds. And the idea here is that one of the features of the operating system is that it has a scheduler that decides which program to run, how long to give it to run, and then when it switches, how to do that switch, and then which program to run next. That's probably an entire chapter out of an operating systems textbook, and that's about all we're going to do in this course right here. And just to give this idea of the memory virtualization a little more context, because all of the programs think they can use any address between 0 and the maximum, they have a shared address space. Memory is just a linear array of memory addresses, and programs can access pretty much any of them. So the question here that motivates this discussion is, what if program A is going to write to address 0xF0A? It's going to put a 10 there. And then what if program B wants to write to that very same address, 0xFA0, and put a 20 there? We need to make sure that that does not mess up program A when program B overwrites what A has written. In truth, each of these programs does indeed have their very own virtual address space, and the details of making this work are taken care of by the operating system. The secret here is that the addresses used by the programs, those memory addresses, are not the same as the actual physical addresses of the physical memory, my RAM chips. The operating system is going to let us treat the memory that the program sees as physical memory. So I wasn't really lying. This is how it works. The program, this is what they see. But it's an illusion created by the operating system. Somewhere in the operating system and the memory management unit on the motherboard there, we keep track of this mapping where the memory for each program that's used is actually really stored in physical memory. So like these addresses right up here in main, they've got these addresses that the programmer sees. This is what's in assembly. But then there's a memory management unit that says, okay, this block of addresses right here actually appears somewhere else in the physical memory. It may be down in this space, somewhere in the 0x300s instead. So anyway, we're going to take a block of memory stored in physical memory, and all of these addresses get shifted to a real physical memory chip. And we just have this mapping table that keeps track of that. And again, that's about an entire chapter from an operating systems book that you guys will spend a ton of time on. Oops, I've got a slide out of order here. This was supposed to come earlier when I was talking about CPU virtualization. But anyway, here's the idea. I have one physical CPU, and I want to run two programs. So program A has the illusion that it's got the CPU all to itself. So I've actually got this labeled as like virtual CPU A. Program B thinks it's running on its own CPU, and it's essentially got access to a virtual CPU, and the operating system takes care of that. So they each have the illusion, it's a trick, that they have their own CPU. There is only one physical CPU in my picture, and the operating system is going to use time sharing to create this illusion. So let me tell you a little bit more about how this is going to work. First, I want to talk about the basic unit of abstraction that an operating system is going to see, and that's known as the process. Processes here. So we've been working with programs the whole time so far. The program has code and data. It's stored, so this would be like global data. This is going to be stored on disk. But the moment we launch this, the loader is going to load it into memory, and the operating system is going to start managing the resources that it uses. It becomes what's known as a process in operating system vocabulary. This is when we actually build the heap and build the stack. When it's stored in memory, we don't need to keep track of any of those details. These are all only important while the program is running. Okay, so at this point, once it becomes a process, it's running, the CPU is executing its instructions. It's a living entity, a process. The stack and the heap are going to grow and shrink. We'll move through the instructions. And so what we need to do is keep track of all of the resources that processes are used. Because when I switch from one process to another, I'll need to know what's going on with all these things. And I'll need to store this information so that the next process can use the registers and use the address space. And the other resource that's going to be important for us to store is the open files. That input-output idea, I'm not going to talk much about it, but it'll be yet another chapter in your operating systems class. So the process has these resources. That's the stuff I'm going to need to keep track of and the information I'm going to need to save when I switch processes, which is the very next topic. How do you switch processes? So initially, the operating system will be running. And at some point, the operating system is going to choose one of the available processes that we want to run and go ahead and turn over control to this, of the CPU to that process. Its instructions are going to be executed. And then at a certain point, we'll switch back. So we need to keep track of the state of all of these resources, the resources used. So those are going to be registers, the memory, including the code, data, stack, and heap, the address space. Essentially, those should be together. And then the list of open files that we're working with. When we switch from one thing to another, if there's room for both programs in memory, then we don't need to worry about anything. We'll just have that mapping, relocate things to a physical memory that's available. If we have an enormous program, if I'm running some sort of game with amazing graphics, it might need all the memory on my computer. Or if I'm doing a really enormous calculation, I might be using the entire memory space. In that case, I need to decide which pieces, if I've got memory that's used by other programs, to get rid of and evict them, just like we would do with the cache memory problem. And again, the idea here is this is going to be a little small. It's a bigger deal because we've got to store the memory that's on RAM on the hard disk, which is a long, slow process compared to everything else. So switching to something like that is a much bigger deal. And the operating system is going to choose exactly what happens there to take care of this and be as efficient as possible. And again, we'll see that there's a lot of different policies by which we can choose what things to replace. So when we switch processes, this is essentially pretty easy. The operating system is going to choose process A to run next, and then it's going to have somewhere in the operating system code a jump that's going to take it down to the instructions wherever we left off from A, or the first one if we're just launching a new process. So both of these things are going to be in memory, or we may have to bring this in as part of that jump to the next instruction as it restores the state. This is also known as a context switch, where we're switching from one program to the other. There's a little more to it than that. What happens when we want to switch back? I'm pretty sure that during the course of my entire program career, I have never written anything that says, okay, I'm going to take a break. My program can just chill out for a minute. We can return it to the operating system. And then I'm sure they'll give back control later. In fact, one of the early operating systems actually did have a yield command, and it was up to the programmer to return control back to the operating system. That was the yield command in one of the early Mac OS systems. But this requires that all processes play nice. I got a typo there. All right, we'll fix that next year. That means that every program that's ever been written has to return control to the operating system and can never have an infinite loop. I don't know how many times I have written code that has infinite loops. I do it all the time. I write code with bugs all the time, and I'm pretty sure that at some point during your programming career, you guys have too. What really needs to happen is the operating system needs a way to regain control without relying on a programmer to say, okay, it's been 10 milliseconds or however long we want. I need to give back control and let the CPU run and execute a different program. So the way this really works is computer manufacturers and writers of operating systems have added hardware support in the form of what's known as a timer interrupt. So basically a timer interrupt is just a clock. It's going to be set by the operating system, and when the timer dings, when we're up, when we used our 10 milliseconds or 1 second or however long the operating system has given our program, what we'll see is that there is a hardware interrupt known as a timer interrupt that's sent to the CPU. So in my example here, I've got some instructions. We do instruction 1, instruction 2. We call a function right after this instruction. We just did number 41. The interrupt arrives at the CPU. What this does is immediately resets the instruction pointer to an address where I have code set there by the operating system known as the interrupt handler. This code, and I just have dots here, I'm not going to go into more details. What it's going to do is initiate that context switch. It's going to take all of the memory that we have here, stash it somewhere safe, so the contents of the registers, what memory is being used, what the open files are, all of the information associated with a particular process, the state of that program. It's going to stash it somewhere safe, and then it's going to choose which program to run next and how long to run that for, and then switch to that particular program. So this is one of the very important ideas, is the idea of this timer interrupt. So okay, so these are the two CPU virtualization mechanisms. First one, the timer interrupt. Basically, a few more details, just let me get a monologue for a minute. When the computer boots up at boot time, when I push the power button and everything comes up, operating system is the first thing that's going to be loaded. The operating system software is going to tell, all right, it's actually more complicated than that. You'll learn about operating systems. The operating system is going to tell the hardware the location of the interrupt handlers. And there's more than one kind. The timer is the main one we're going to focus on here. But we also have input-output interrupts. So if I type something on the keyboard, it sends an interrupt to let the operating system know that there's now text waiting in the keyboard memory buffer. Same deal with the disk. It takes a very long time to read or write to the hard disk. And so a lot of that is just taken care of. It's a connection between the RAM and the hard disk. And what we'll see is that it takes a long time, and when whatever transfer operation is finished, either the memory or the hard disk, that system will send an interrupt and just let the CPU and the operating system know that that job is finished. Okay, so at the very beginning, we tell the hardware where the interrupt handler code is, the code that actually does the context switch to a different program. And the operating system it's basically just a clock that's going to produce signals every 10 milliseconds. And I'm using that roughly. I have no idea how long it is, but it seems like it switches pretty fast back and forth. And the operating system just sets that up and then is going to take advantage of every time our 10 milliseconds are up. It's going to go in and decide, do we want to give this program more time? Do we want to switch? So there are some problems here, though. The first one is that the timer can be switched on and off. And this is an advantage for the operating system. The operating system wants to get its entire job done, switching the memory out, storing the registers, making sure that I've got code that decides which process should run next, and it does not want to be interrupted while it's doing that. So as soon as the operating system takes back control, it's going to switch the timer off. And the other thing the operating system can do is it can change, the address of the timer interrupt code. Okay, so this might be important if I want to switch from one kind of policy to another. If I want to say, this process won't take very much time, or this process needs like a lot of reading to the disk, and I can choose what policy I'm going to use for these different types of situations, depending on what I've seen as the code executes so far. The problem is, what if a user process switches off the timer? All right. I personally know that as a programmer, I am extremely greedy. And if I thought my code will run faster if I just didn't wait around for all these other programs to run, and I had the power to turn that timer off and then, turn it back on when I was done, I would do that. Absolutely. But that's not good. So what we're going to do is actually prevent the user from switching off the timer by instituting one more hardware solution. This is known as privilege mode. The idea is here we're going to have a status register. that's going to have a bit that either says, if it's set to 0, we're in user mode. If it's set to 1, this is going to be known as kernel mode. If you haven't heard that word before, the kernel is just the core piece of the operating system. It includes like the scheduler that decides which program to run, the code that takes care of this memory virtualization where I map, this is the memory used by program A and it's stored in this physical location, either in RAM or on a disk somewhere. It knows where things go. There's also things that are not considered part of the kernel. The device drivers, input, output, those things don't need to be operating in kernel mode. I certainly don't want to get the manufacturer of my graphics device driver the power to take over more than it needs to. So the idea here is that when kernel mode is set, I'm over here with a 1 in the status register, any instruction can be executed. And that includes stopping the timer. It includes the special command that restore all of the pieces that a particular program needs and then jumps to it. Those sorts of things. There's a couple other things. You will learn more about it in operating systems. So anyway, the major example here, turning the timer interrupt off, is a privileged instruction, and those can only be executed when the kernel bit the privilege mode bit is set to 1. All right, and the last topic I want to include in this lecture is the idea of the process state. So every process is going to be in one of 3 states. Right after the operating system gives control to a process, so process A is going to be said to be running if it's the CPU is actually executing its instructions. After its 10 milliseconds are up, the timer interrupt is going to send a signal that returns control to the operating system through that interrupt handler. And then the program is said to be descheduled. And it's going to then just wait for its turn again in what's known as the ready state. After some time, the operating system may choose to bring this process back in. It might choose something else. But the process, when it is brought back in, is said to be scheduled, and it returns to this running state. At that point, it's going to execute its instructions. All right, the third state that we can actually run into is for a process that's waiting for something. And that's going to be known as something that's blocked. This will almost always happen if we ever begin an input-output instruction. For example, if I want to read something from the keyboard, I prompt the user, I wait for them to enter something in. Or if I want to read a large file and it needs to go retrieve that from disk, these operations all take a bunch of time. And rather than just letting the CPU just spin its wheels or just wait for something to happen while me, the user, is not bothering to type very quickly, I wanted people to use that time to go take care of some other business. I'm going to schedule a different program. So when something is blocked, it's no longer running. Essentially, like being descheduled, we've stored all of the important information from the registers and the memory it's using and the open files, and we'll bring in a different ready process. So once we've blocked something, as soon as that the user types whatever they need to and pushes enter, or I finish moving the file into memory so it's ready to go, I can switch this process back to a ready process. And from there, we can continue, eventually the operating system will say, okay, it's your turn again, and then it'll take advantage of whatever keyboard buttons I pushed or whatever file I loaded. So the question is, can I go backwards here? Can I go from ready to blocked? And the answer is no, because I need to actually request some sort of input-output, something that I need to wait for. And that's going to be a CPU instruction that says, go grab something from the keyboard. If it's ready, over here in this blue ready circle, that means it's not running. The instructions are not being executed. Something else is running. This process is just waiting for the operating system to give it its turn. We also, depending on how the operating system is implemented, we will rarely see that the process goes from this block state back to running. Almost certainly it's going to switch to a ready state after the input-output operation is completed, rather than evicting whatever is running immediately and returning to executing those instructions. All right. Yeah, that's going to do it for this lecture. I'm going to go put this together, edit the video, merge all these little clips into something coherent, and then yeah, again, it's been a real pleasure teaching this class. I've really had a great time doing this. I still have a couple more things. I've got some more final regrade requests and some project regrade requests that I need to address. And then I'll be putting out grades probably later this evening. I'm leaving town tomorrow, so I will be out of contact. I'm not going to have cell service up in northern Wisconsin or internet. So I'm hoping to get everything taken care of before I leave town. The other thing is, if you're excited about operating systems and want to learn more, I will be putting a whole bunch of reading resources with this block on the Canvas website for the course. So you guys can, if you've got some spare time before classes start again in 3 weeks and want to take a look at that, it'll be very exciting for you. All right, it's been great. Have a great semester in the fall, and I hope someday this whole COVID thing wraps up and you guys can come visit and I can meet you in person. Have a great day.